Hello everyone, welcome to Recitation 0T about losses. I am Dareen Harthi, and in this recitation I will go through the importance of losses. I will explain different kinds of losses, how to choose the right loss function, and PyTorch implementation of losses. So what is a loss function? A loss function is a function that measures how far is the predicted output from the desired output, and it is provide feedback for the neural network to improve its prediction. So during the backward pass, in neural network training, the loss gradient is computed and propagated back through the network to update the weight and to minimize the loss. The choice of a loss function will impact different things in neural network training. It can impact how fast the training converges. So different loss functions can affect the speed at which model converges to a solution during training. Some loss functions may enable faster convergence, leading to a reduced training time. Also, it will impact how resilient is the optimization against the stochasticity in the batch. Some losses are very sensitive to the randomness in the batching process, such as contrastive losses, because these losses depend heavily on the specific pairs of examples in the batch. So randomness in batching can lead to a significant variance in the loss values and the gradients, potentially affecting the stability and efficiency of the learning process. Also, it will impact model performance because the loss function guides the training process by quantifying the difference between the predicted outcomes and the actual values. A well-chosen loss function ensures that the model learns effectively to improve its accuracy and reliability. Some of the must-used loss functions are cross-entropy loss. Cross-entropy loss is widely used in classification problems, especially when dealing with multiple classes. It measures the performance of classification model whose output is a probability value between 0 and 1. The second one is binary cross-entropy. Binary cross-entropy is a special case of cross-entropy loss for binary classification task. And the third one is L1 loss, also known as mean absolute error. This loss function is used in regression problems. It measures the average magnitude of errors in a set of predictions without considering their direction. L1 loss is less sensitive to outliers compared to MSE or mean squared error, which makes it useful in real-world scenarios where outliers are common. The last one is hinge loss. Hinge loss is commonly used in support vector machine models for binary classification, but it can be used in any binary classification task. This loss function is designed for maximum margin classification. It penalizes predictions that are on the wrong side of the margin threshold. So how to select the right loss function? The selection process of the loss function can depend on different factors. Depend on problem type, the model architecture, the nature of the dataset. So for problem type, usually people use in regression tasks mean square error or mean absolute error or Hopper loss. Mean squared error is the average squared difference between the estimated values and the actual values. Squaring the errors gives more weight to larger errors than smaller ones, which can be desirable in some scenarios where larger deviation are particularly undesirable. Mean absolute error are easy to understand because they are in the same units as the output variable. Hopper loss is a combination of MSE and MAE. It behaves like MSE for small errors and like MAE for large errors. For binary classification tasks, we will usually use binary cross-entropy and hinge loss. Binary cross-entropy is favored when the model output probabilities and you want to penalize wrong predictions that are made with high confidence. Hinge loss can be used in neural network for binary classification problems. It is particularly useful when the goal is not just to classify, but also to ensure a confident separation between classes. For multi-class classification, category cross-entropy and sparse cross-entropy KL divergence are usually used. The difference between category cross-entropy and sparse cross-entropy is that for CCE is the input is usually one hot encoded vector. So all the values are 0 for different classes except for the class which represent the current input. And for sparse category cross entropy, the input usually are the labels are integers. So this are the major difference between these two. For KL divergence, it is usually used to measure the difference between two probability distributions. The second factor is model robustness. For model robustness, you might consider using Huber loss or mean absolute error. MAE is more robust to outliers as it treats all deviations from the true values equally. Huber loss is less sensitive to outliers than MSE, yet not as robust as MAE. So the fourth factor is optimization and stability. The implementation of cross-entropy in PyTorch is a combination of log softmax layer and negative log likelihood. This combination is more numerically stable than applying softmax followed by a log and the computing the cross-entropy. The log softmax step is in the cross-entropy loss helps to avoid numerical instability issues that might arise due to the exponential function in the softmax, especially for large input values. Also, you might consider for if you have class imbalance in your dataset, you might consider weighting the underrepresented class. People usually use weighted cross entropy or focal loss to balance the classes in the dataset. You might consider different factors based on your problem requirements and the domain of the task. In deep learning, people usually experiment with different losses. Losses is a hyperparameter. So you might try different losses or combine different losses together to train the neural network. PyTorch offers two kinds of implementations: functional implementation for losses and the module implementation or class implementation for losses. The difference between the two implementation is that for functional implementation, you can invoke directly the function itself without initiating an object from the class. So the function are invoked directly. They are stateless. They don't retain any information between calls. This makes them highly flexible, allowing you to perform custom operations easily. They are particularly useful for simpler models or when you need a straightforward custom loss computation. For class implementation or module implementation, you have to initiate a subset from the object class, and these objects are stateful, so they can maintain information across calls, which is useful for certain loss functions if they have learnable parameters. They align well with PyTorch design, making them easier to integrate with other components, with layer definitions, or with any other components in PyTorch. And it makes the code looks cleaner. So when should you use each? For the functional implementation, when you need a quick direct loss calculation, especially in less complex models, you might consider the functional implementation. For the object-oriented implementation, um, it can be used for complex models where you need seamless integration with other components, or when your loss function needs to maintain a state or learnable parameters. So if you notice in this example, they have the same behavior, they produce the same output, but in some cases you might prefer the functional definition or the class definition. So it depends on your style of code or your own problem. So in summary, the choice between them depends on the complexity of your model and your specific requirements. For simpler direct control, functional is ideal. For integrated stateful loss computations, in complex models, you can go with the NN.modules or NN modules. So thank you so much for your attention.